During this presentation, we have to talk about stationary state. To understand more about the stationary state, please read out this definition. The state in which the probability density is independent of time is termed as stationary state. We know the value of probability density, that is P of r comma t, which is equal to absolute square of psi of r comma t. Psi of r comma t square is psi star of r comma t into psi of r comma t. This is the formula for probability density. But in the case of stationary state, P of r comma t is given by absolute square of psi of r, which is equal to psi star of r into psi of r. Here, which is independent of time. Position probability does not depend on time. Now, we have to prove this by considering the Schrodinger time dependent wave equation. This equation is modified as h psi equal to E psi. Equation 1 is presented in this form. Since the value of Hamiltonian is minus h cross square divided by 2m del square plus v. This is called Hamiltonian operator. Then the energy operator E equal to IH cross dou by dou t. So the equation 1 is expressed in this form. H is Hamiltonian operator, then the quantity IH cross dou by dou t is our energy operator. We have expressed equation 1 in terms of relevant operators. When the Hamiltonian is independent of time, the solution to equation 1 is given by the product of spatial coordinates and time. See here, psi of r comma t is expressed in terms of psi of r. Psi of r is independent of time, and f of t. Now the equation 1 can be modified by using the value of psi of r comma t here. So instead of psi, we have to put f of t into psi of r. Now equation 1 takes this form. Minus h cross square by 2m del square f of t into psi of r plus v of r in f of t psi of r equal to IH cross dou by dou t f of t into psi of r. Now divide all the terms of equation 3 by f of t into psi of r. See here, the space coordinates del square operator is dou square by dou x square plus dou square by dou y square plus dou square by dou z square is operating on psi of r. Therefore, f of t is a constant. Here, dou by dou t is operating on f of t. Therefore, psi of r is a constant. So, equation 3 takes this form. In the case of v of r, f of t psi of r, if you divide the term by f of t psi of r, only v of r is present. But in the first term, if you divide the first term by f of t into psi of r, f of t cancelled out, but 1 by psi of r del square psi of r is present because the operator del square is allowed to operate on psi of r. It is a variable. So we have kept this term as such. If you come to the right hand side, dou by dou t is an operator which is allowed to operate on f of t. So that 1 by f of t into dou f of t by dou t is present. Psi of r is a constant, we cancelled it. Now in equation 4, take this 1 divided by psi of r as common term. Therefore automatically we may multiply this v of r by psi of r. which is equal to 1 by f of t I h cross dou f of t by dou t. This is our equation 5. In the equation 5, LHS is a function of psi of r and RHS is a function of f of t only. Therefore, each side must be equal to constant, say E. Here E is a number, total energy. Now, the left hand side is equal to E. Now, this is modified as minus h cross square by 2m del square psi of r plus V of r psi of r is equal to E into psi of r. Now, this is our Hamiltonian h into psi of r. Already we pointed out that Hamiltonian is independent of time. E into psi of r. Here E is not an operator. This is mere a number, eigenvalue. But previously, while considering this equation 1, here Hamiltonian is an operator, IH cross dou by dou t is our energy operator. But in this equation 6, the 6 may be modified as h into psi of r, which is equal to E into psi of r. Even though the Hamiltonian is an operator, E is not an operator, it is a number, it is an eigenvalue. This is called eigenvalue equation. Now, take the right hand side, 1 by f of t IH cross dou f of t by dou t equal to E. Using method of separation of variables, we arrived at this. IH cross dou f of t by f of t equal to E into dou t. If you differentiate the quantity f of t, we can get the numerator. If you differentiate f of t, we can get dou f of t. So the formula is log of the denominator, the integral formula. For that, keep this dou f of t by f of t, left hand side, then bring this IH cross to the right hand side, E divided by IH cross into dou t. Then 1 by IH cross is modified as I divided by I square h cross, multiply I by I. Multiply this by I. I square is minus 1. So this is equal to minus I divided by h cross. So this is present as such. 1 divided by IH cross is modified as minus I by h cross E into dou t. Now we have to integrate this. See here, if you differentiate the denominator, we can get the numerator. So the formula for integration is log of the denominator. Log f of t, which is equal to minus I by h cross E into t. Integral dou t is t. If you apply the limit, lower limit is 0, upper limit is t, we can get t. From this, f of t equal to e power minus I by h cross et. If you raise the things to the power e, this log cancelled out. So f of t equal to e power minus I by h cross into et. Now the wave function becomes, the wave function is psi of r comma t equal to f of t into psi of r. The value of f of t is this much, e power minus I by h cross into et. Then the psi of r is present as such. So psi of r comma t is e power minus I by h cross et into psi of r. Now come to our definition. We know that the probability density P of r comma t is absolute square of psi of r comma t, which is equal to psi star of r comma t into psi of r comma t. If psi of r comma t is e power minus I by h cross et into psi of r, then psi star of r comma t is e power plus I by h cross et into psi star of r. Now multiply these two things, this and this, we can get psi star of r into psi of r, because e power IE by h cross into t into e power minus IE by h cross into t is equal to e power 0, that is equal to 1. See here, P of r comma t is absolute square of psi of r. which is independent of time. Now, we do this. For a stationary state, div j equal to 0. Here j is the probability current density. It is noted that the particle is not to be necessarily at rest in the stationary state, because in the stationary state, the expectation value of momentum is not necessarily 0, which is an important point, and we may go to the conclusion. A state with a well-defined energy therefore has a wave function of the form psi of r comma t equal to e power minus ie by h cross into t into psi of r, and for such a state the probability density is independent of time. Such states are known as stationary states. That's all about the stationary state.